Welcome to section 5.4 on the conditional probability and general multiplication rule. This is part 1 of this particular lesson. So a conditional probability denoted by P of F given E for that probability. It denotes the probability of event F occurring given that event E has already occurred. So with that being said, do note where that location of the event E is in this particular denotation. It is after that given symbol to note that that is when it has already occurred. So, to give a brief example of it, just so we know what's going down. Example number 1, suppose a single die is rolled, right? What's the probability of rolling a 3? Right, so we want to roll 3. Well, there's only one 3 on the die. So it only occurs once out of a total of 6 possible sides, right? But let's say before rolling this die a second time, we are told the outcome is an odd number, right? So we're told it's an odd number, and we want the probability that a roll is a 3 by that point, right? So we want the probability of rolling a 3 given that we were already told that this is going to be an odd number. Right? So based upon what we know from this then, there's a total of 3 odd numbers on a die, right? 1, 3, and 5. And only one of those numbers is a 3, so numerator is still 1. But as you can see, knowing there was an odd number increased our chances of obtaining a 3. So that same idea applies, right? Where if we have E and F being different events, then again, to note what this symbology means, this is the probability of F given E has already occurred. So given E has occurred. Again, make note of where that event E is, right? E has already occurred. It's after this given symbol. And you could see that the probability that actually is the probability of E and F, right, here in this numerator, divided by the probability of E. Or, depending if we have a contingency table, this is the number of values in E and F divided by the number of values in E, right? And I highlighted all those E's to denote that since E has already occurred, that is the event in the denominator, right? So based upon that, we could then find the probability. So given a contingency table for this, such as the one I have here on the screen, we have, based on the table of United States residents aged 15 years of age or older, we want the probability a randomly selected individual has never married, given that the individual is male. So this is the probability of never married, given that the individual is male. So, based upon that last slide, this is the probability that we have a never married male, or never married and male. Both mean the same thing. So never married male divided by the probability of being male, aka the event after this given symbol. So since we have those values from the contingency table, I'm going to use those instead of the actual probabilities, since the denominators are going to cancel out anyway. For the number of never married males, we look at our table, it's 40.2. divided by the probability of being a male. So we're going to add up the male column, and that is 117.8. Tossing this expression to a calculator should give us a probability of about 0.3413. So with that being said, with some algebraic manipulation, we could have the general multiplication rule. So if we have two events E and F, the probability that E and F occur at the same time is the probability of E times the probability of F given E. Again, E being that event after the given symbol. Must match. So for an example of that, I want the probability a driver who is speeding gets pulled over is 8/10. The probability a driver gets a ticket, given that he or she has been pulled over, is 9/10. We want the probability of randomly selected driver who is speeding gets pulled over and is given a ticket. So this is the probability of speeding and given a ticket. Per the last slide, this is the same thing as the probability of speeding times the probability of being given a ticket given that this person has sped. Again, same exact event after the given symbol. So doing this just amounts to multiplying. The probability of speeding is 8/10 times the probability of being given a ticket given that the person was speeding is 9/10. So 0.8 times 0.9 gives us a probability of 0.72. About 70, I shouldn't say about, of 72%. Here's another example. Suppose that I have 100 circuits sent to a manufacturing plant. 5 of them are defective. The plant manager randomly selects 2 and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. We want the probability the plant manager discovers at least 1 defective circuit and rejects the shipment. So this is the probability of at least 1 defective. So applying that the complement rule to this, due to the at least in that statement, this is the same thing as 1 minus the probability of the complement to at least 1 being defective is the probability of less than 1 as being defective. Or the other way to write that would be of 0 being defective. Or the other way to look at it is 1 minus the probability that neither of them are defective. So what does that mean? This is the same thing as 1 minus, this is the probability of 1 minus the probability of the first one not being defective. Not defective times the probability the second is not defective. Given the first one was not defective. So, what is this? This is 1 minus the probability the first was not defective, right? So there's a total of 100 circuits at this point. And to find the probability the first one was not defective, there's a total of 5 being defective. So that means there's 95 not defective, right? Times the probability the second's not defective, given that the first was not defective. Because the first was not defective, there was a total of 100 circuits previously. Since we already chose one circuit, the total number of circuits now, one was chosen, that means there's 99 left over. And because there were 95 non-defective circuits before, after choosing one non-defective circuit already, there's now a total of 94 left. So this is 1 minus 95 over 100 times 94 over 99. Tossing that expression into a calculator, we get 0.098, or 9.8%. Let me know if you have any questions or concerns, and be on the lookout for part 2 of this lesson. Thank you.